turn time. Let's get started. Okay, so today we're talking about kinetics, and I think the first thing, at least in chemistry, what you want to do is you want to question why you have to learn this topic. Now, in the case of kinetics, it's really easy to answer. I think there are like 4 common questions that everyone asks when they start learning about chemistry, and that's like 1, how fast does a reaction occur? 2, how much does a reaction occur? 3, why does a reaction occur? I said 4 things. Oh my god. Okay, so there are 3 common things that everyone asks about, and kinetics like happens to answer one of those 4 questions already. 3 questions already. How fast does a reaction occur? So, and you'll learn about the other 2 questions. In particular, for how much does a reaction occur, you'll learn about it in equilibrium, which is the next unit. And then how much does a reaction occur is something you'll cover in thermodynamics. So yeah, and my computer crashed. That is amazing. Specular, I love it. All right. So moving on. That is not what I wanted. Okay, so if you've attended our last unit session, then you may have heard me emphasize this concept of macroscopic level and microscopic level in chemistry. Does anyone remember that? If you don't, raise your hand. I'll take that as a no. Okay, so and in the case of kinetics, I think microscopic and macroscopic also applies here. Because macroscopic and microscopic behavior tends to be different, you have to be careful about which perspective you're talking about. So macroscopic properties results from a collective behavior of microscopic properties. That's just a review session for you. And this is really no different for kinetics. So on the macroscopic level, we often talk about how fast a chemical reaction occurs overall. But on the microscopic level, we talk about how fast a reaction occurs on the molecular level. So that would be collisions. And we'll be talking about collision theory in much more detail later. So yeah, keep these in mind and don't forget about the difference between macroscopic and microscopic. You'll honestly never see an exam that explicitly talks about macroscopic and microscopic, but it is definitely going to help you have an understanding of chemistry overall. Okay. Any questions? All right. So give me 1 second. Let me. All right. So moving on. We're going to talk a little bit about rate laws next. Thank you. Okay, so let's talk a little bit about reaction rates. So basically, how I like to think about reaction rates is that they're like a quantitative value that represents how fast a reaction occurs. And it's basically, it's best to compare reaction rate with speed, not velocity, speed, because the first thing you have to know about reaction rates is that they're a scalar value, not a vector. So they don't possess a direction and have to be positive. Because it would be kind of stupid if you said something like the average rate of consumption is negative, because that would mean that it's forming, which is weird. So it gets confusing if we introduce a direction into reaction rates. So what chemists like to do is keep most reaction rates positive if possible, right? So if speed tells how fast an object is going, like what the difference of the distance, or I don't know what word they use. I'm being a bot here. Anyways, so if speed tells how fast an object is going, then reaction rate tells how fast a reaction is occurring. It's very similar. But how do you measure a reaction rate? Well, concentration probably makes the most sense because, well, the faster a reaction occurs, the more drastic change the concentration of the reactants or the products would be. And I hope it makes sense. Okay. So some of the things you want to keep in mind with reaction rates is that I've mentioned this 3 times already, but reaction rates are never negative. Kinetics tend to avoid negative values because negative values indicate direction. Reaction rates are not a vector value. They are a scalar. They only represent how fast a reaction is occurring, whether it be a forward reaction or a reverse reaction. So here, you might see that I have a negative value here. And that is because, oh, okay. So Alice asked the question, what is the difference? Sorry, what do you mean by what is the difference? Oh, do you mean when I was talking about distance between macroscopic and microscopic? Okay, so here, I'll go back to the slide where I was talking about that. So on a macroscopic level, we know that reaction rates are independent of the coefficients of the chemical equation. And that is because reactions are a collective behavior of microscopic properties. And in this case, what I mean by that is that there are mechanisms, like there are elementary reactions that lead to the overall rate law and chemical equation. Does that kind of make sense, Alice? Okay, cool. So, as I was saying, right, so the average rate of consumption here is a negative. Why do we put a negative value there? Well, because if it's being consumed, you would assume the concentration final minus concentration initial, which is basically delta R, would be negative. So we put the negative value here to make this overall positive. Does that make sense? And in the case of the average rate of formation of P, then this would already be a positive value, so we don't have to do that. Okay? So basically, what you have to take out of this is reaction rate is always positive. All right. So one more thing. In terms of reaction rate, not rate law, you have to consider the stoichiometric constants, not stoichiometric constants, stoichiometric numbers of a chemical equation and report the species to make sure your rate is correct. So here, what is the difference between R and P? Right, so here I did technically forgot to report the chemical equation I'm referring to here, which is a bad thing, and your teacher will hate it if you do that. So this currently is showing an example of a reaction, well, a hypothetical reaction of R becoming P. Does that make sense, Samantha? Okay, cool. So, right, so you have to consider the stoichiometric constants of a chemical equation and report the species to make sure your rate is correct. Okay, so if we consider something like form of ammonia, right? Yeah, no problem. Something like this, right? In this reaction, let's say that the rate of consumption of nitrogen gas is just 1. That's not the correct units, but whatever. In this case, it makes sense that the rate of consumption of hydrogen gas here would be 3 times greater than nitrogen, and the rate of formation for ammonia would be 2 times greater than nitrogen. It's similar to just stoichiometry, right? Now, one way chemists like to avoid reporting the species is something called unique rate, which is basically dividing all the stoichiometric constants. This is basically saying stoichiometric constants that would give a unique rate for one particular chemical equation. Now, I don't think you actually have to know this, but it's just something you can keep in mind. Okay, moving on. Okay, so how do we measure reaction rate? And what is Beer's law? And why do you learn it? Okay, so Beer-Lambert's law is very important in kinetics because it creates a relationship between the absorption of light by a material and the concentration of a colored solution. So I think absorption is something that's kind of a concept hard to understand. So I'll give you like a brief analogy, and that's something like colored glass, basically. So think of the colored solution as colored glass for a moment, although glass technically isn't really a liquid solution, but whatever. The more concentrated the dye is in the glass, then it's harder to see through the glass, right? And it's basically because the absorption of light decreases with concentration. Okay, so we've established the relationship between concentration and absorption. Okay, but there's also one more thing we can learn from this analogy, and that is, well, how thick the colored glass is. The thicker the colored glass, isn't it like harder to see through than a thin colored glass? Yeah, so we established that length is also related to absorbance with that analogy. Something to keep in mind. Okay, so what does Beer-Lambert's law have to do with kinetics? Well, it basically gives us a way to measure the change of concentration. The change of concentration now relates to the change of absorption of light, which is something, you know, computers will deal with, but you still get the point. Okay, I would like to mention that the reaction must release some form of light, but this doesn't have to be visible light. It can be like ultraviolet or infrared. But what we use in the high school chemistry lab typically is UV vis, or ultraviolet visible spectroscopy, which basically detects light from the ultraviolet to visible range. And right, so any questions? I'll take that as a no. All right. Instantaneous rate of reaction. How many of you are taking a calculus class or have taken a calculus class? Can you raise your hand? Okay, about half of you. That's fine. All right, so basically, this is a concept you'll learn in calculus. It's called a derivative, and I suck at pronouncing that, but whatever. So basically what it is we know that the average rate of reaction is equal to something like delta R over delta T, right? But this is a curve, and a curve can't really accurately predict. I mean, a slope or a tangent can't really accurately predict over, well, the slope can't really accurately predict what the rate is over this entire curve because it's the average. So what we like to do is see from A and B how this time interval, right? We make this smaller and smaller. So this time interval gets smaller and smaller until it becomes so small. It's basically like, you know, well, it's just extremely small, infinitely small. This time interval is approaching zero, basically. And that is when we call it the instantaneous rate of reaction. And I think that should cover what you need to know about this for now. All right, so any questions? Any questions? I'll take that as a no. All right, so we just talked about reaction rate. Cool. Now, what the hell is the difference between rate law and reaction rate? And why do I need to learn this? Great question. Okay, so there are two things I want you to notice. The difference between the rate law and the rate of reaction. And I've illustrated both of the equations here. Okay, so the first thing is that the rate law is independent of time, unlike the reaction rate. So we know that as time proceeds, the concentration of reactions decreases because how I talked about the instantaneous rate for a second there. So we know it decreases as time proceeds, therefore the rate of reaction decreases. Why? Because these concentrations decrease, and overall the rate of consumption would also decrease. Okay, so, and this is basically a continuous process as the rate of consumption or production really approaches a certain value. Now, I think a really good question to ask here is why not zero instead of a certain value? And this is something you'll cover in equilibrium, but basically in chemistry, there's no such thing as a dead reaction. It is just that the forward reaction rate and the reverse reaction rate is the same. And, oh, what? Could you repeat that one more time? My audio cut out. From where? The difference between rate law and reaction. Yeah, sure. Okay, so the first thing I want you to know is that the rate law is technically independent of time, at least in the equation. We know that as time proceeds, because I just talked about the instantaneous rate of reaction, we know that the concentration of reactants decrease, therefore, the rate of reaction decreases as the reaction proceeds. And so, yeah, that's basically what I said. And I was talking about how the rate of consumption or production approaches a certain value instead of zero because there is no such thing as a dead reaction. Is that fine, Alice? Okay, cool. All right, so are all rate reactions random? No, um, they aren't technically all random, although it might seem like it, because if it was really all random, then chemistry wouldn't exist. Okay, so the initial rate illustrates a relationship between the initial concentration. And what I mean by this is basically the initial rate is proportional to the initial concentration. Now, why does this make sense? Because, or at least why is this not present in other times? Why does it have to be initial rate? That's because as the reaction proceeds, you get products. And if you have products, those products might actually undergo something called a reverse reaction. And that makes kinetics kind of complicated. So if we measure the initial rate of reaction, then because we don't have those products that, disturb the rate of formation, we can actually make a meaningful relationship out of it. So here, this shows the initial concentrations of 4 trials. And we can see that these are the same. But let's say at time here, these differences are vastly different. So we can't, it's hard to create a relationship with this. And the initial rate is very meaningful here. Okay, I'm repeating myself. All right. Any other questions? Is the rate of disappearance the same as rate of consumption? I'll answer your question later. But basically, the rate of, oh wait, the rate of disappearance, the rate of consumption, yes. Okay. So, order. Let's talk about order. So, order is, each reaction has basically a unique order, and it is the number that is the power of concentration. So in this case, it'd be N and M. This is basically the ones I circled. Yeah, that's order. Okay, so order is something that we determine experimentally. So if, for example, N was equal to 2, then it would be second order in A. If M was equal to, let's say, 1, then it would be like first order in B. And if N was equal to 2 and M was equal to 1, then it would be second order in A, first order in B, and third order overall. Could you see that one more time? Yeah, sure. So, this reaction would be considered first order in A. So first order in A. Something like this would be second order in A, first order in B, and third order overall. Okay, so if you see these 3 graphs, then yeah, no problem. So if you see these 3 graphs, they illustrate the difference in order. So see how this is a quadratic function, and this is a linear function. As you can see, the rate in this case is in the y-axis, and assuming a constant, then the concentration is on the x-axis. So I hope that makes sense. And this is something called a zeroth order, that's when the rate of the reaction is independent of the concentration. As you can see, this is the concentration of reactant, not the rate of decomposition. And we see that it's decreasing steadily. Okay, any questions? All right. So, okay, here I've given a lot of examples for a lot of reactions. So something like this, combine hydrogen and iodine, we get hydrogen iodide. The rate law in this case is this. Cool, wow, okay. But there is something you have to be careful of. Just because the coefficients in this case are 1 doesn't mean the rate law order will be 1, or just because, you know, it's H2 plus I2, the rate law would be something like this. Just because, you know, 2 products combined doesn't mean that your rate law will be second order, and we'll talk more about this later. This is the reverse reaction of the reaction we just saw, and it seems that the rate law in this case is second order to hydrogen iodide. All right, and all these, you can look back at it later in the PowerPoint that I'll send you in Schoology, so don't worry about them. Any questions? You don't have to think. We'll talk about the temperature dependence later, but okay, moving on. Integrated rate laws. All right. Okay, so here I'm going to talk a little bit more about physics. So remember when I said how reaction rates were analogous to velocity or speed? Well, it's the same case here. As you can see, this velocity time graph, I'm not sure, but in physics 1, I am fairly confident that the area under the curve of velocity from, in this case, time 0 to time 5, this area is equal to, let's say, what's it called? Distance traveled, right? And as velocity is basically, velocity measures the change of distance, then the rate of reaction would measure the change of concentration. So if we calculated the area under the graph from time something something, and then the reaction rate, then that would equal to concentration. That's basically how integrated rate laws are formed. Okay, cool. Next. Now, I would derive all these equations, but for the sake of simplicity, I won't. But if you do know calculus, then I hope that the information I just gave previously should be probably less than you would need, but I mean, probably less than you would need, but well, you can just email me if you have any questions about that. Anyways, so integrated rate law, an equation that allows you, well, they're very useful equations that let us calculate the concentration of reactants or products at any time after the start of the reaction. And yes, they're very powerful. So these graphs, one thing to note, well, actually, three things to note here. This plot is very important, and the distinction here is very important. So make sure to not confuse these. For example, if you're looking at a plot where it's concentration versus time and the plot is linear, then it's zeroth order. If it's a natural log of concentration versus time and it's linear, then it's first order. Same business with second order. But basically, we know this because if this is y, if this is x, then this is the slope. And the same case for here. Oh. Huh. Interesting. Well, that's unfortunate. All right. Make sure to write this equation down. This is probably the better way. This is y. This is a, you know, the y-intercept, and this is the slope. So that makes sense, and the same case for here. So for second order, if it's 1 over concentration versus time, and you see a positive linear slope, then you already know it's second order. Okay. And half-life. How half-life is, how like these equations are formed, especially this one, which we use the most, is we just plug in a arbitrary value, or here. So let's say that this is equal to 1, and we know half-life is the amount of time it takes for something to decompose exactly half of its concentration. So it would be 0.5 here. If we plug these values in to the integrated rate law for the first order, right? Right. Okay. So we know that this is the same thing as this, which is the same thing as ln2 equals negative kt. So t would equal to ln2 over k. Now I'm not sure why there's a negative here, so I must be doing something very wrong. But all right, I'll fix that later. Okay, so reaction mechanisms. Okay, before that, does anyone have any questions? This lecture seems pretty scuffed, especially with my computer crashing and me not having my notes, but is everything fine? Is everyone doing well? Everyone's good, right? Okay, cool. So temperature and kinetics. Let's talk shortly about the Arrhenius equation. So this equation is important for two main reasons. First, it shows a relationship between rate constant and temperature. Rate constant and temperature. So as the temperature increases, this becomes less negative, right? And therefore, wait. So this becomes less negative, and overall, this would become greater. So that basically means as temperature increases, the rate constant increases, therefore increasing the overall reaction rate. Second, it shows a relationship between activation energy, which is basically the minimum amount of energy required for products to form, and rate constant. So let me erase that for a sec. Activation energy and rate constant. So as activation energy increases, then this overall becomes more negative, therefore this becomes smaller. Okay, but there is also another thing I actually want to show you, and that is, hold on a second. Whatever. Okay. Here. Let me share my window for a sec. Okay, do you guys see this? Oh, okay. I'll assume you guys do. Oh, here it is. Nice. So this is the Arrhenius equation where this A, which we like to call the pre-exponential factor or the collision factor, is equal to 2,500. I set that constant just so that I could visualize this. So in this case, this x-axis is actually temperature, and this y-axis is the rate constant, basically. And as you can see, at activation energy, when it's 10 kilojoules, you can see that as temperature increases, besides this very small hump here, where it drastically increases, it basically stays constant, like even if you increase temperature. But as activation energy increases, we can see that there is more curvature here. So as temperature increases, the rate constant becomes more and more, well, so as activation energy increases, that means it is more temperature dependent. Does that make any sense? Are you good? Okay. Let's move on to collision theory. So, collision theory is basically explained by the name. It is a theory that reactions occur just based on collisions between molecules. So we talked about gas laws in the last lecture, and basically we know that temperature is related to the average kinetic energy. I just put the equation here just in case you forgot. This equation right here. Okay, so we got that established. What's another thing from gas laws we need? Well, that's the Maxwell distribution, or the Maxwell-Boltzmann distribution, whatever you want to call it. See how like the average molecular speed increases as the temperature increases, and like the intervals of molecular speed become wider. And you know that speed is related to kinetic energy from right? Huh? So as molecular speed increases, that increases kinetic energy. Okay, cool. So for, let's say, for a certain reaction to occur, let's say that like you need about this much kinetic energy. Then, as you can see from the Maxwell distribution, we know that at 300 Kelvin, barely any, well, sorry, I was highlighting 100 Kelvin, but at 300 Kelvin, there is about this amount of molecules that will be able to react or undergo reaction. But for 600 Kelvin, there's this many reactions that can undergo reaction, which is substantially greater. I hope that makes sense. All right, so, well, why does molecules need to have activation energy or a certain amount of kinetic energy for a reaction to occur? Well, first of all, repulsions are a thing. Like repulsions between molecules are a thing, and they raise potential energy. And once they contact, like once the two molecules contact, the potential energy becomes substantially greater and becomes maximum. And molecules that don't have enough energy are just going to be repelled because of the repulsion. But for those that do have enough kinetic energy that can overcome the increase in potential energy, basically, these shaded regions are those molecules that can overcome the potential energy barriers and react into products. You know, this can be applied to not just gases, but basically everywhere. Not like the Boltzmann distribution thing, but like the reaction rate thing. Although, sorry, I meant Maxwell Boltzmann distribution. Those are two different things. Well, right. So this is basically why as you increase temperature, reaction rates will also increase. And this is why when you cook meat, for example, at a higher temperature, it cooks faster. Okay, so one random question you might have is, well, why can't we just cook our steak at like 3000 Kelvin or, 5000 Kelvin? Wouldn't that be like an instant cook? And if that was your question, then great job. You stole my words right out of my mouth. I don't know. Okay, so the reason why we can't do this is because increasing temperature doesn't just increase the rate of reaction for favorable reactions, but it increases the reaction for all reactions. This means that unfavorable reactions will also get faster, which is a bad thing, which is why we can't just, use the highest temperature for everything. All right, so let's mention these graphs on the right. I'm sure you've seen them a lot in biology and in your chemistry classes. This graph is something we like to call a reaction profile. And in the case of A, we know that the reactants have a lower potential energy overall than products. So the amount of heat released is endothermic. And this makes sense with this relationship yet again. Why? Because if you think about it, so the endothermic reaction is basically a reaction that consumes heat. And since kinetic energy is related to temperature, right? And the increase of potential energy partially cancels out the kinetic energy of molecules because conservation of energy. And a collective behavior of these microscopic reactions would lead to a decrease in temperature. And we see that the potential energy is higher than the reactants. That means that some of the kinetic energy was converted to potential energy. What does that mean? That means temperature was lowered because there is now less average kinetic energy of the gas molecules. Does that make sense? And okay, so moving on, the reverse, or for an exothermic reaction, it's still the same. It is a reaction that releases heat. Since kinetic energy is related to temperature, it might seem that some kinetic energy is required to overcome repulsions between molecules. But we see that the products are much lower in potential energy than reactants. So all that potential energy lost must be converted into kinetic energy, which basically means increased temperature. Okay, which one? For exo or endo? Sure. So basically, for exothermic, sure. So for exothermic, it is a reaction that releases heat. And since kinetic energy is related to temperature, with the equation above, it might seem that some kinetic energy is required to overcome repulsions between molecules. And that's true, because as you can see, there's about this amount of activation energy that is required by the molecule. But we see that the potential energy of the products is much, much lower than the potential energy of the reactants. So therefore, at the end of the reaction, we know that all of the potential energy lost must be converted into kinetic energy because of conservation of energy, which basically means increased temperature, because we know as this increases, then we can justify that the temperature would also increase. Does that make sense, Alice? Cool. All right. I think that's it. And then elementary reactions, I'm already over the hour mark, but it is fun because we will have another review session tomorrow. I mean, next week. So elementary reactions. Elementary reactions are basically the most simplest reactions that can occur. And by simple, what we often refer to is reactions that occur on a molecular basis, meaning it involves 1, 2, 3, 26, 69 molecules, and not bulk matter. It doesn't involve a billion molecules, is basically what I'm trying to say. So that being said, because elementary reactions do not deal with bulk matter and they don't involve phases, they are individual molecules, you see that elementary reactions don't have phases. Here, so in a normal reaction, we would have, like, I don't know, a gas phase, but in this case, we don't. And this is a mistake you probably don't want to make. Right, so there are no phases involved in an elementary reaction. I hope I made that clear. And what's nice is that a combination of these elementary reactions, and this only works because we're on the microscopic scale and we're not looking at the collective behavior of molecules. So what we like to call a combination of these elementary reactions, which is called the reaction mechanism, must result to the overall chemical equation. So that's basically making a connection with microscopic and macroscopic. So basically, what happens in the microscopic level like all of those mechanisms that turn reactants into products is now being generalized to the macroscopic scale with the rate laws and stuff. So basically, all the intermediates or whatever is formed by elementary reactions must be canceled out and result the same as the chemical equation, and the rate laws must result the same. If that was confusing, don't worry, I'll talk more about it when we're doing problem solving. So now we've just made a connection between I said that, I'm sorry. So, but something to note is that just because your mechanism is same as the rate law that was determined experimentally doesn't mean that it's 100% correct. There could possibly be another mechanism that gives the same rate law but has different elementary steps. Does that make sense? Any questions? Any questions? All right, so I would like to make a slight disclaimer here in that you never, under any circumstances, want to assume that the chemical equation will help you find what the rate law is. This only applies to elementary reactions. Now, what I mean by this is, if we assume these are elementary reactions, they would probably lead to the same equation, assuming that they are a one-step bimolecular reactions. So basically, that'd be a hydrogen gas molecule. Well, no, not gas, but an H2 molecule and a Br2 molecule colliding together. That would equal, rate of reaction, rate equals, rate constant times H2 times Br2 in terms of concentration. But that is not the case for a chemical equation. And you can see how drastically different these two reactions are, even though they seem very similar. They're halogens, and they have the same number of stoichiometric coefficients. But this implies that the mechanism that they undergo is totally different, judging by the rate law. Does that make sense? All right, so next question. We are finally almost at the end of our content review. Okay, so this basically, here's an example. Okay, see the reaction that I just mentioned. It's it's H2 molecule and I2 molecule colliding together to form hydrogen iodide. Okay, cool. And they kindly gave us the rate of reaction, which says that it's second order overall. So, where's my pen? So it's H2 and I2. And they also gave us two mechanisms to work with. So it could either be a one-step reaction where two molecules. Oh my god. I would like to mention that these mechanisms are not supposed to have any phases. This is illegal. So when an H2 molecule and an I2 molecule collide, that would be something we would call a bimolecular reaction. And I guess I forgot to mention what molecularity is And what that basically is how many molecules is involved in this collision. So, okay, I think I have to go back here. Go back a little bit more than that. Okay, so in this case, molecularity 1, it only involves, so this is common decomposition, or you'll see this commonly in a reverse reaction where products is decomposing to reactants. But I don't think for AP chemistry you really need to consider that, but I'll mention it again next week if you decide to come. So molecularity 2 involves 2 molecules. So it could either be A and B, which results in this, or it could be A and A colliding, the same molecules colliding together. And the rate would be second order in A. And then there's also 3 molecules colliding, and these tend to be very rare. So if you get any of the mechanisms that propose a tertiary reaction, you should probably question that mechanism. But sometimes it does happen. Sometimes. But it's very rare. All right, so 2 mechanisms are proposed here. So this is an elementary reaction, so phases disregard. So here it would be like this, right? But here we get introduced something called a fast equilibrium, or a fast reaction and a slow reaction. So, okay. We know that this is fast equilibrium, and equilibrium basically means it's basically rapidly converting into one another, or this reaction, this back and forth reaction is occurring rapidly, is basically what they're trying to say. So that being said, if it's an equilibrium, it means that the concentration of this and this would always be equal until another reaction, let's say the slow step of this reaction, which is this I intermediate, right, attacks a hydrogen gas. Or two of these reactive I intermediates collide with a hydrogen gas molecule. Now, why is this the slow step? Because tertiary reactions tend to be slow. Well, they tend to be unlike because they're very slow. Because imagine the probability. So sorry. It's fine, Kate. I'll release the recording later. So basically, imagine having 2 molecules collide into one another. That's already kind of unlikely if you think about it. But imagine having 3 molecules simultaneously trying to collide in one another. That's even more unlikely. Therefore, the reaction rate would be much slower for a tertiary reaction, right? So basically what this fast equilibrium means is that as this decreases, more of this will be formed by this. So basically, you can think of it as this can basically convert into this very quickly. If this is lost, then okay, I think I'm confusing you guys now. All right, so let's talk about the rate determining step. What is the rate determining step? Well, it's obviously the slowest step of the reaction. And what that means is basically the one that has the highest activation energy. So, comparing this activation energy with this activation energy, you can see that if a molecule has enough kinetic energy to overcome this activation energy barrier, then it will easily go over this activation energy barrier, right? And it's the same story for this one. This activation energy barrier, basically everyone can overcome, but this is the real deal. This, not a lot of molecule, this is basically what is, the rate determining step. It is what determines the rate. So, in this case, this is a fast step. This occurs really fast. So it doesn't require that much kinetic energy to overcome the activation energy. So, when we try to calculate, when we try to propose a mechanism, do we take into consideration of the rate of this fast step? So do we have to take into consideration of this? No, because it's a fast step and nobody cares. But in this slow step, where it's like this, now this is the real deal. This requires a lot of activation energy, or more precisely, it requires collisions to happen more frequently so that there is a higher probability of 3 molecules altogether colliding. And one of the best ways to do this is increasing temperature, therefore increasing kinetic energy, therefore increasing velocity of the molecules. Because if you think about it, if the molecules are traveling at a faster rate, then, well, they have more chances of collision. I hope that makes sense. Oh, and here I would like to mention that, as you can see, this is different from this. Why is that? Well, as you can see, remember how I said that this concentration is basically determined by this, right? So this is the slow step, and if some of this is, deplenished, then this will just automatically make this again very quickly compared to this. So the rate of production of this is basically the concentration of iodine overall. Why can we make this? Because we can basically say, in this case at least, that iodine is the same thing as 2 iodine radicals, or iodine atoms. Does that make sense? I'm sorry, this was really confusing, so I'm kind of worried that that didn't make a lot of sense. Okay, any questions before we... Oh. Wow, I got totally skimmed. That's very nice. Okay, so I guess we'll talk very shortly about catalysts, but can we do that format? Yes, only elementary reactions. Okay, catalysts. Catalysts are basically a substance that increases the rate of reaction without being consumed in the reaction itself. So it lowers the activation energy of any reaction. But since it only lowers the activation energy, it means that not only reactants, the reaction rate, the forward reaction rate is faster, but the reverse reaction rate is also faster. So does it change how much a product is formed? No, not really. It just makes it faster. It makes the reaction go faster. And another thing to keep in mind is that the higher the surface area of the catalyst, the faster the rate, because there are more places for the reactants to actually, well, in this case, let's say, there's more chances for the reactants to adsorb to the metal surface, and therefore that would make it easier for the other molecules to collide because one of the molecules is secured in place by a catalyst. And that's how catalysts work. I think in biology, they call it the induced fit mechanism. But I'm not sure if you need to know that for AP Chem. All right. I think that's all for content review. So let's talk a little bit about problem solving. Are we good on the content? And I will try to give a brief overview next week as well, just so that we don't make too many mistakes. Any questions? Excuse me. All right. So, problem type 1, reaction rate definition. All right. So, it says the temperature is irrelevant here. Right out of the bat, I can tell. Nitrogen dioxide decomposes to nitric oxide and oxygen. In one experiment, the concentration of NO2 decreased from 0.01 moles to 0.005 moles. Okay, so we already know the delta concentration of NO2 is equal to negative 0.0050 moles over the course of 100 seconds. So what is the average rate of disappearance? Well, we can just use the exact same equation, the consumption equation. But one thing to consider is that, again, reaction rate in kinetics, we only try to work with positive values in terms of the reaction rate. It doesn't mean that you convert literally everything into positive. That would be just wrong. But so we know that this would be the average rate of consumption. So if we plug these values in, it would be 0.050 moles and then 100 seconds. So what's the answer? Oh, wait, hold on. Actually, it might be smart to make a poll next time here. Hold on. Let's make a poll. So this is the next question. If you would work on it, that'd be great. Here's your choices. I'll give you about a minute. Do you guys need more time or? Okay, I'll give you 1 more minute. Let me use the bathroom for a second. Ten, 9, 8, 7, 6, 4, 1, 2. Okay, I think that's enough. So C is the overwhelming choice. All right, let's see. So, how to tackle this kind of equation and this kind of question? Well, we know that there are only two species that are considered reactants. So in the rate law, we know that it has to be this kind of format, right? Well, it doesn't have to be, but it's most likely going to be with the rate constant. So one way we can figure out like the rate law of this following reaction is to compare two of these data values where one of these concentrations of the reactant species are held constant. That being said, in this case, as you can see, this is being held constant, right? And in this case, we know that the initial concentration of B is actually 2 times greater for experiment 2 than experiment 1. So we would, and the initial rate states that this, because of this only single difference, the initial rate actually doubles. So what does that imply? Well, rate, so we already know that the rate is proportional to, well, the initial rate is proportional to B, right? To the first power. So it is first order in B. Okay, let's look at A. But in this case, it's a little bit more complicated because both A and B are changed for experiment 3. Now, here we know that A is multiplied by 2 times and B is multiplied by 3 times. So we already know that this initial rate is going to be 3. Okay, so we already know that this multiplied by 3 multiplied by the order of, well, no, not the order, but basically we know that it's already going to be multiplied by 3 because the concentration of B is already in first order. Okay, so what does that result? Well, the answer that we get is actually 0.2 0.06. I believe that's actually incorrect though. 0.085 times 3. No, 0.255 is what we get when we multiply this by 3. So from here, we know that this and this difference is basically half. And we know that this and this difference is basically half. So we can already justify that the concentration of A is in first order, or first order in A, because the initial rate is proportional to the initial concentration of A. Now, there is a more general way of doing this, and that is basically, well, comparing the two mathematically in an equation kind of thing. So that would be like this, right? Where we plug in two different values, but what is it? One of its concentrations are constant, like this case, so we can cancel them out. So what we would be left with is, well, let's say it's 0.1 in this case and 0.2 in this case. We'll be left with this and whatever the initial rate is, right? Now, you might question, well, why don't we put the rate constant? And that's because it's a constant, and unless temperature changes, it's not going to change, so we can cancel those out because it's in the same reaction. Does that make sense? Cool. So, problem 3. And that is rate constants. So, especially in kinetics, but in... Oh, okay, sure. So, here. Let's just use the mathematical way for now. So, do you agree with this, Alice? Okay, cool. Well then, because, let's say, for example, if any of these concentrations for both experiments are the same, for example, in the case of A, if it's both held at 0.05, right? No matter what the order is, it could be 1 to 14, this will still cancel out, technically, because it will always equal to 1. Because 1 to the 14th power is 1, and 1 to the 1th power is 1, and 1 to the 3rd power is 1, right? So what we're doing is we're trying to discard one of the variables, so this could be just a single variable equation. So basically, if we plug these two data in, it would be something like 0.085, 0.170. Okay, cool. So here we know the rate constants cancel out. So, and we know these two cancel out because they're the same concentration, initial concentration. So in the case of B, it's that, and then it's that, right? Okay, cool. So this is basically the same as this, which is the same thing as this. Now, this is equal to 1/2. So what is 1/2 to the m power equal 1/2? So what is m? M would equal 1, right? So that would be first order in A or B. Yeah, first order in B. Does that make sense? Yeah. All right, so rate constants. I really want to emphasize units in kinetics because a lot of people tend to get mixed up with that. So, okay, I'll give you about 2 minutes to solve this question. Okay, go ahead. Does anyone need more time or? Okay, I'll lock the result. Oh, nice. Okay, so I think that's enough. So this is kind of surprising, but uh, as you can see, they gave you the rate law of reaction. It says the rate is rate constant times, well, it says 0th order in X and 0th order in Y. That basically means the reaction rate is independent of the concentration of both the reactants. what does that mean? Well, in this case, well, we know that the reaction rate is moles per second, correct? So if the rate law is basically K, then we should also expect that K is equal to moles per second. So the answer would be A. Now, this was kind of, I guess it was a trick question, but let's say for something like a first order overall reaction, right? Something like this. Then we know that the rate has to be moles per second. And we know concentration is moles. So if we divide moles per second by moles, we only get per second, or 1 over seconds, which is the rate constant. So in first order overall reaction, the rate constant is just seconds to the negative first power. And for second order overall, then, well, this would be moles to the second power, and if you divide it, then we get, moles, well, 1 over moles times seconds. So it'd be 1 moles times seconds, right? So there's kind of a relationship you could probably see here. Basically, from zeroth order reaction overall starts with moles per second, and then as you increase the order, the moles actually also, the power of the moles decrease by 1. Does that make sense? Or not moles, but molarity. Cool. Yes, exactly. All right, so integrated rate law. The first thing I really want to emphasize is that you shouldn't just try to plug in numbers into random equations and assume that you'll get the correct answer. And I think this is true for the integrated rate law and many other equations in chemistry and probably physics. But basically, in this case, it's kind of plug and chug. If you remember what the equation was for the first, sorry, we're running out of time, so I'll just do all these questions, and you can try the unit packet that I'll be giving out today later. Basically, we're given the rate constant. So just from units, because it's second to the negative first power, we know that this is going to be a first order overall reaction. Well, it's given here, but whatever. It says if the initial concentration of the substance is 1.50 moles, and we're given T, which is 500 seconds. Okay, and we want to figure out what the final concentration is. Okay, so we can basically just use the first order integrated rate law, which is, well, this guy. All right, so plug numbers in. This ln 1.50 m minus k, put that in the calculator, and then t, put that in the calculator. And let's see what we get. ln 1.5 minus 6.7 Make sure to take the natural log out. And what I'm getting is 1.07 moles. Did you guys get that? Just say in chat. How do you take the natural log out? Great question. All right, so if you calculate this, this should be 0.07047 or something like that, right? So ln what this basically is it's log e to ant and then 0.07407, right? So we could express this in terms of e to the 0.07047 power equals concentration of AT. So calculate this and then you should get this. Does that make sense, Sarah? Okay, cool. Next question. Integrated rate law, this time a little bit harder. All right. A sample, so you're given the initial concentration already, which is 0.9, well, it's not really concentration, but you're given the amount of NO2, but where it decomposes irreversibly to N2 and O2 in a first order reaction. Okay, so we know that the reaction, the rate constant is going to be seconds to the negative first power. Okay, cool. After 42 minutes, 42 minutes, cool. T equals 42 minutes. 0.640 moles of N2O remains. So we're given the final concentration of N2O as well. Another first order equation, so it would be something like this. Now, let me rearrange this. Like that. And let me rearrange this again. So do that. Now, if we plug numbers in here, the rate constant I got is, let's see. Oh, and here's a little bit of a tip. We don't know the volume of this container, but why can I just plug in the mole values here? And that is because it's this and this occurs in the same container. So volume is constant. If we know volume is constant, then we know these two cancel out. So it's really meaningless to try to find volume. We can just divide the moles and still get the correct answer. So, you know, neat thing to know. All right, so initial concentration says 0.9, final concentration says 0.64, and time 42 minutes. So my rate constant is 0.00812 seconds to the negative first power. And then what you want to do is, it says, how long will it take for the reaction to be 90% complete? So that means that only 10% is remaining in the final concentration, right? So let's actually use this equation again. This equation
but use it in terms of time equals t. All right, so we know, let's just say that there was 100 molecules as the initial concentration. Now, I justified that if the volume is the same, then we don't really have to consider volume, right? So if 90% is complete, then there's 10% of reactants left. So there would be 10 molecules left, right? What is this equal to? That is 10. All right, so instead of this, we just plug in 10. Easy. Well, not really, but, and then we plug in the rate constant and we get our answer. Does that make sense? All right. Actually, it might be meaningful to screenshot this, so I'll give you, or actually, you can look at the recording later. So, all right. So graphs in order. For the irreversible reaction A goes to products, the graph of 1 over concentration of A as a function of time is linear. What is the reaction order in A? Can you guys answer this question in chat, like right now? Yes, it is second order. I hope you guys are good with this. This is a pretty typical answer or typical question. All right, so elementary reactions. They give you the mechanism. The first step seems like a fast equilibrium, and the second step seems like the rate determining step. It's the slow step. Cool. So we know that this is the slow step, so this will basically determine the reaction rate. So rate will equal to NO and NBr2. But what do we see here? Oh, NOBr2 is not a reactant. It is actually an intermediate. As you can see, although it is produced, it is destroyed by the second reaction. So overall, it does not appear in the chemical equation. Why? This gets canceled out. And if you add these together, you get 2NO plus Br equals 2NOBr. Very cool. All right, so we know that NO and Br2 is basically the same thing as NOBr2, right? So we can, instead of plugging this in, we can plug this value in. So that would be NO to the second power and then Br2. Now, why can we justify this? Because it's in equilibrium, and equilibrium means the forward reaction rate and the reverse reaction rate is the same. And it's the fast step, so it doesn't really determine the rate of the reaction. So yeah, does that make sense? So we can say that the reaction rate, the correct answer would be B, right? And here it asks what NOBr2 is best described as. An intermediate and product, a homogeneous catalyst, and heterogeneous catalyst. So I haven't really mentioned what homogeneous and heterogeneous catalysts are, but basically homogeneous catalysts are catalysts which substance exists with the same phase as its reactants. So for example, if it's a reaction that involves liquids, and if it's a reaction that involves liquids, then the catalyst would also be a liquid. But if the reactants are gas and the catalyst is a solid, then the solid catalyst would be a heterogeneous catalyst. But in this case, it isn't a catalyst because, well, in order for something to be considered a catalyst in a mechanism, it has to be present first as a reactant, and then lastly, it has to be at least reformed as a product. Does that make sense? But in this case, because NOBr2 is directly made by the reactants, it is considered an intermediate. Okay, so here the answer would be A. Cool, very cool. All right, elementary reactions moderate. This looks amazing. So they give you the chemical equation. This is actually an equation you'll learn in organic chemistry if you decide to take it in college, but nobody cares. For the reaction, it says the rate, it gives you the rate law. So the rate equals rate constants times terp butoxide and a hydrogen ion. All right. So we know it's first order in terp butoxide and first order in acid. So it's second order overall. With which mechanism is this rate law consistent? Let's look at A for a second here. So this indicates equilibrium. Great. This is the slow step, so we know that what we're going to get is here. We're going to get something like this. And because this is an intermediate that is involved in fast equilibrium, we can substitute that for, well, this. Now, does this look like the correct mechanism? No, this is a terrible mechanism. This is incorrect because it involves the chloride ion, which makes 0 sense. So A is incorrect. So let's look at B now. B looks like it has 3 elementary reactions in its mechanism. Okay. So the slow step is the second step, it seems. And the slow step is determined basically by the concentration of this only. I'm too lazy to write this out. But because this intermediate is also in fast equilibrium with this, we know that this can be substituted with this. So in B's case, the rate law would be K and then CH3. We call this terp butoxide, but and would you look at that? This looks the same as this. So the answer would be B. Now, for these two, I'll leave it up to you guys to confirm. And then we have our last problem type, which is about catalysts. Blackboard is dysfunctional. Let's go. All right, catalysts. In which of the following ways may a catalyst increase the rate of a reaction? Now, I actually do want you guys to answer this question, so I will open up a poll and see what you guys think. And it seems like we almost finished in time, so that is amazing. Okay, so if you have an answer, feel free to okay. Hold on, let me make the poll. Okay, there we go. If you have an answer, feel free to put it there.
to the 3 people who answered C as their answer, I'm assuming you remembered something from biology, because that is correct. So I think for everyone, everyone can agree that a catalyst may decrease the overall activation energy. I mean, I guess that makes sense because, well, that's what basically catalysts do. But why can it alter the rate law? Well, if you think about it, catalysts basically provide another way for a reaction to occur. And what that means is that there is another mechanism that is involved with a catalyst when a catalyst is introduced. That means because there is a different mechanism, that probably means that it is possible for it to have a different rate law. So, and I think another question that would be very good here would be, can a catalyst can the catalyst create more products? And that would obviously be false, right? And I think the last thing I do want to emphasize about elementary reactions is that, let's say that you have a mechanism, right? And the mechanism is in accordance, or it matches the experimental rate law that you got, correct? That does not mean that your mechanism is correct. There can be multiple mechanisms that involve different elementary reactions but end up with the same experimentally determined rate law. So your experimentally determined rate law can support your mechanism, but it can't prove your mechanism. Does that make sense? All right, so